there. So let's talk about the fact that the roller coaster actually makes it, around the loop. It's in multiple places. They tend to focus on top and bottom, but you should be able to tell me about any of the places where the roller coaster cars could be. Because in any of these places where the roller coaster cars could be, there are forces acting on the cars. So although the problems tend to focus on just the top and the bottom, don't be surprised if I ask a question that isn't about the top and the bottom. I think that A, B, C, D, and E are all excellent locations where I can ask you what's happening to the cars. And you should have quite a few things you should be able to say about them. So like I said, problem number 5 focuses you, but the first thing I would hope you could tell me is that the velocity of the car at the bottom is probably the greatest. Slows down as it makes its way to the top. And that it's probably traveling the slowest at the top. And that's just gravity. You throw anything up into the air, it travels slower as it goes up, and it speeds back up as it comes back down. That's gravity. So I would expect you to be able to talk about the fact that the velocity of the cars is always changing. That has nothing to do with centripetal force and all that other extra stuff. That's just a fact of gravity is pulling down on the cars. In addition to that, you should be able to tell me that the force of gravity is the same on the cars all the time and is acting downwards. I know it seems ridiculous, but you guys start talking yourselves into weird circles on these problems, and you know what I'm talking about. You know that you start to confuse yourself. But the force of gravity is always downwards and is the same size everywhere here. It's the normal force that is the elusive idea here. And it's the normal force that I need for you guys to become more equipped at talking about. The weight's going to be constant. But the normal force is a responding force. I keep saying that in class, and I'm not sure it's really sinking in. I want you to be able to say it on the test, and nobody really does. But the normal force responds to the circumstances. It has to. If the normal force can't respond here, then basically you're saying that the track breaks because it can't apply the force it needs to. But generally it responds. Now, the response of the normal force here is to provide an unbalanced force towards the center of this circle. There has to be an unbalanced force towards the center, or there will be no circular motion. But even not knowing that, it should be clear the direction of the normal force in each case has to be a radial direction. It has to be, because it has to be perpendicular to the surface. So no matter where we are, the normal force has to point towards the center because the track is circular. A perpendicular to a circle lies along a radius. That's geometry. So I see no reason why I couldn't ask you to draw the free body diagram for any of these places. But I could focus the mathematics on E, C, or D and feel just fine asking about any of those places, even though your problems have focused only on C and E. But no matter which place we are, and this is critical, no matter which place we are, all of them must have a net force equal to MAC for the part of the force towards the center. This isn't X or Y right here. And I'm going to say it very clearly, for the part of the force toward the center. This is the only way the object travels in a circle, is if it has a part of the force towards the center proportional to this. And that's true every place on this track. Now, the problem focuses you by talking about E and C specifically, and they want you to know that at E, the normal force has to be bigger than the weight. Why? Because there has to be an unbalanced force towards the center. That's why they want to focus you on that idea. At C, they want to focus you on the idea that you already have a force towards the center and you don't need a normal force there. The normal force is there in case you need it. In case you're going so fast, you need more force than what gravity alone can do, right? This balance right here. You go really, really fast as long as you have enough force to make you turn. But at the top, there is this possibility that you could be going too slow. Right? You have two forces acting towards the center. But if you start going too slow, one of these responds, the other one stays fixed. So the weight stays fixed. The normal force responds. It can get smaller as V gets smaller. But there's a limit, meaning the normal force can only go to 0 and then disappear. That's when you're no longer touching the track. That's an important implication, that there is a minimum, a speed to which you can't go any lower, or else you're no longer in circular motion. Limit problems like this are big deals on the exam. I am going to ask one. Probably in a multiple choice, because you could memorize this. At this point, my expectation is that once you've seen this once, they're all the same. So you should be able to just memorize what's happening here. At the bottom, though, it's a little different. There is no minimum or maximum. If we look at the bottom, the normal force points up towards the center. The weight is downwards, and that equals mv squared over r. Even if you're not moving, that just means the normal force equals the weight. There's no minimum. I can go as fast as I want as long as the track can provide the force. Now, I could also tell you, this is at E. This is at C. But you could also be asked about D. There's no reason why you couldn't. You've got net force is equal to the normal force, and that equals mv squared over r. There's also a component of the force downwards. That's just speeding the car up. But you could find the normal force from the car if you knew how fast you were going there. I probably wouldn't ask anything mathematical about A or B, because there's a component of the weight towards the center that makes it pretty complicated. So I won't talk about that. I might talk about that in AP Physics C, but that's not really a discussion for this class. So that's the roller coaster question. And there's lots of pieces to it. Now, they wanted you to do something that was a little bit unrealistic in my estimation. They wanted you to make a comparison of the normal force to your weight. That's what the question asks. And that means they want you to solve for the normal force at the bottom. I'm sorry, normal force to the weight at the bottom. To do that, a comparison is a fraction. And they told you the fraction they wanted you to compare, normal force to weight. So you had to divide both sides by weight. That way I get a comparison of the normal force to the weight. Now, you had to go the extra mile then, probably, and distribute that mg and recognize that it was mg divided by mg plus mv squared divided by mgr. And then maybe, that's 1 plus v squared over gr. That's what they wanted as an answer. Now, I won't ask this question on a test like this. If I was to ask this question on the test, what I would likely do is I would say, how fast would you have to be going to feel 3 times your weight? That's how I would ask it, just so you know, because that's more AP style, which means I'd be asking a question where I was telling you the size of the normal force. And I'd want you to solve for the velocity due to that normal force. So if I say you're experiencing 3 times your weight on your test question, I'm telling you the normal force on you is 3 times mg. I would know that for your next test. I'll say it again. If I say that you're experiencing 3 times your weight, or 4 times your weight, or 2 times your weight, I'm telling you to replace normal force with that multiple times mg. Be ready to do that. Your experience of weight is the normal force. All right. Is that pretty thorough? Covered it all? All right. So I'll throw it back to the floor. Is there another one you guys want to see? Anybody at home?
Could you do 7?
I hope so. Wouldn't be much good as your teacher if I couldn't. You never know. So let's see, number 7. Determine the gravitational force that one body exerts on the other. Assume that the moon's orbit on Earth is circular, ignore interactions with other masses. Okay, so determine the gravitational force that the sun exerts on the moon. All right. All right, so there's 3 questions there, and I'll tell you a little bit about how I would probably react to this question if I was writing it. So we've got the sun. That's not the sun. The sun should be sunnier. So how about we go with the sun? And then the earth. Gotta make the earth earthy. And the moon. But the moon is tiny, so. Now this is not drawn to scale, but here's the sun, earth, and moon. The first thing they wanted is the force on the moon from the sun. And the first thing I want to be very clear about when it comes to gravity is that when you're finding the force on one object, you're finding the force on both. Remember, the gravitational force is the product of 2 masses. So this force is the force that both objects experience. So in question 2 and 3, where they're asking the force on the moon from the earth and the force on the earth from the moon, it's the same question. So it's the same answer. There's no extra work there. Once you have found one, you have found them both. Now, I think this problem misses an opportunity to ask you something else. And I'll talk about what that is here in just a minute. But the first thing they asked was for you to find just the force on the moon from the sun, which would be the mass of the sun times the mass of the moon times g over their separation squared. Remember, this r doesn't stand for radius, it stands for separation distance. And that's from the center of one object to the center of another. Be careful with that. There's easy ways to trip you up on that. Now, I could plug the numbers in here, and I don't really know who asked the question. Do you need the numbers plugged in to get the answer? Or is that enough for part A? Well, I'm asking the person at home. I don't know who asked, though. Who asked this question at home?
I mean, the way it was on the homework, you had to put in the values.
So that's what I'm asking is, you want me to go through the process of putting the values in? So this is going to be 1.99 times 10 to the 30. 7.35 times 10 to the 22nd. And then 6.67 times 10 to the negative 11th. I left the units out. And we need that separation distance too. And I don't have this one memorized, but they say 1.5 times 10 to the 11th. and this is squared. Your biggest problem here is you got to put all this in your calculator, and that tends to be hard for you guys because you're going to get something and you really are not going to have any idea if it's the right answer or not because you don't know what to compare it to. So I want to show you a little trick, and it's not a trick so much as just the way math works. For just a moment, only look at these numbers. Because they're exponents, when you multiply these things together, you add the exponents together. And when you divide, you subtract the exponents. So just look at the exponents. I have 30 and 22. Add that together, I get 52. Subtract 11, and I get 41. So the top is times 10 to the 41, give or take 1. Right, because I have 7 times 6. So that's probably going to go up to 42. But just put down to 41 for right now. The bottom, I have 11 squared, so I have to double it, which means it's times 10 to the 22. Now, when I look at that, that means my answer is going to be times 10 to the 41 minus 22, which is approximately somewhere around times 10 to the 20. If you do this ahead of time, I know it takes longer, but if you do this ahead of time, you're far more likely to get the right answer. Because if you put garbage into your calculator, it will give you garbage out and you'll have no idea because it's just some number with an E and some other number. You're going to have no idea. It's going to be big. Now you have an idea. And this will help because one of the most likely things you'll do is you'll forget to square it. And this is an easy way to pick up that you forgot to square it. Now, you have to actually go through the process of putting it in your calculator. And I can't help with that. I do want you to recognize that when you're putting it in your calculator, you better be using the EE button. You have to be. Now, there are ways to do more of this in your head. Like I said, 6 times 7 is 42, times 2 is 84. So I think the top is around 85. And the bottom, 1.5 squared. Well, 1.5 squared is, not a big deal. It's like 2.5. So you can get pretty darn close to the actual answer. So I bet the answer is like 40 times 10 to the, 40 times 10 to the 20 or 4 times 10 to the 20. I think it's 4 times 10 to the 20, to be honest with you. Just looking at those numbers. But you have to plug it in. So I'm hoping you guys are doing that. Anybody get the answer yet? 4.33 to the 20th. And this is a force, so it's newtons. These big numbers like this, I don't want to see you guys get an incorrect answer on a test because you can't use your calculator. You can know all the physics you want. If you can't push the buttons right, you get one wrong, that hurts my feelings. And I don't really care if you can use your calculator. So they'll tell you that they believe the AP exam can be done without a calculator. That tells you this, no. That tells you this isn't on the test. Right. You're interpreting it the wrong way. Like they're expecting you to do this on the test, and they're not. They're more likely to ask you questions that will give you expressions then, as opposed to numerical answers. So that's something to keep in mind, that they don't want, how many minutes do they want you to be pushing buttons? They don't want many minutes to be wasted away pushing buttons. Not when they can ask another question that's about what physics knowledge you have. So mastering will make you push buttons, sure, because it's easier to put a number in than it is to put an expression in. So we have to be considerate of what they're going to ask on the test. So the next question is doing this whole thing over again, but for the Earth and Moon, which changes just one number, well, 2 numbers in all of this. It changes the mass at the center, which is now the mass of the Earth, and it changes the radius you're going to use, the separation distance, because now I need to use the Earth-Moon distance. But the rest of it is essentially the same. So this will be 5.97 e to the 24th times 7.35 e to the 22nd, and 6.67 e to the negative 11th, divided by that distance of 6.37 times 10 to the, oops, I'm doing all e's this time, e to the 6th squared. So let's try this again. 24 plus 22 is 46. 46 minus 11 is 35. So this is times 10 to the 35. 6 squared is 12 times 10 to the 12. Now this is 6. Now, if you really want to see some tricky stuff, I've got a 6 squared, and I've got a 6 and a 6. That all cancels out. I'm expecting my answer to be like 7, maybe a little more than 7, maybe 8. I bet this is like 8. I'm just looking at what's left over. But if you're trying to get a quick estimate, I bet that's pretty close. It also means 35 minus 12 is 23. So I'm thinking it's 8 times 10 to the 23rd newtons. So now I plug it into my calculator. And now I see what I get. Somebody's already gotten it though. What'd you get?
7.21 to the 23rd.
7.21. So these quick estimates, they don't get it right on. They're just designed to help see if you're in the right ballpark. Now, that would be the same answer for the force of the moon on the Earth. So that should work for question B and C as well. This is not what I would ask on the test, though. If it were me, I would ask something a little different than this that wouldn't require any of these calculations, but would ask the same kind of thing. If I was asking this on the test, I would want you to consider where the force on the moon is the greatest and where it's the weakest. Because what this problem didn't do is it didn't really talk about something that's actually kind of important. That the moon is orbiting the Earth. Trying to line these up better, but not sure I'm doing a great job, but it'll do what I need it to do. So there's a time when the moon is over here and it's experiencing a force from the sun and the Earth in the same direction. And there's a time when the moon is over here where there's like a tug of war on the moon between the Earth and the sun. So I would have questions that would ask about where the more likely biggest net force is on the moon. It would also suggest that the moon is experiencing greater centripetal acceleration when it's at B. So it means it goes slightly faster there and goes slower when it's here, which are actually true things. Because the force on the moon is being divided when it's at A, so there's less net force towards the Earth. So it must go slower. But there's more net force towards the Earth when it's at B, so it must go faster. The sun and Earth and moon dance. And they have a dance that goes around the sun. It's a weird thing. And yeah, I expect you to be able to talk about that kind of tug of war, that kind of thing that's happening. That tug of war destroys moons. That's why there's, these rings around planets. These are moons that got a little too close to the planet, and those tidal forces just rip the moons apart. All right, I think that's pretty exhausting discussion of question number 7. Anything else on the homework? 9? So Tanner asked for number 9. All right, so there's 3 things about this problem that I like. There's a couple things I don't like. So the one I don't like is that they're trying to trick you by asking about the distance above the Earth's surface. So let's not be tricked. We're going to be launching a satellite that's going to have some kind of, velocity when it gets up to orbit, and it's going to be in this orbit around the planet. So draw that a little nicer. So there's my satellite. And it's got its tangential velocity like so. Now, I think the first takeaway here is that there are, and this goes to question number 8 as well, there are 3 things that are involved in talking about calculating orbits. And this problem adds a 4th. So I'll put a 0 amount here, something that this problem adds that's really not about finding an orbit. The thing that this problem adds is they want altitude. The altitude above the Earth's surface. That's not the separation distance. So just be aware that if you're asked for altitude, altitude is going to be the separation distance minus the radius of planet. This. I'm putting that at 0, like, because it's not really part of the problem. They just want you to give it in a different format. Altitudes are easier to measure because we're standing on the surface. We're not standing at the center of the planet. So although we calculate this based on the center of the planet, when we measure it, we have to measure it from the surface. So that's why they ask about altitude. But to be honest, everything we're going to do is going to be about R, not about the altitude. So you have to remember to change your answer at the end. So the first thing that we have to recognize is that the only reason the satellite orbits at all is because a delicate balance has been struck between its centripetal, between its tangential velocity and the distance away from the center of the planet. So we start by recognizing that this balance is struck because there's an unbalanced net force towards the center. And that balance begins with this idea of centripetal acceleration. That there's an unbalanced force that causes a centripetal acceleration on the satellite. The next thing is that the force that causes this is just gravity. So the second part of this is the recognition that there's going to be the mass at the center, the mass of the satellite, g, and the separation distance squared. In making this recognition should be a pivotal moment where you stop and make sure that the radius of curvature is the separation distance. They don't have to be the same. I want you to be very clear that they don't have to be the same. And if we get complacent about them being the same, that's when I zoom in and make a whole different question where they don't have to be the same. So the first example I would give would be the fact that binary stars don't orbit about one star with the other one going around it. Binary stars are 2 stars that could be the same size, and they orbit about a point between them. So the separation distance is different than their radius of curvature. So I want to be very clear that you should always ask yourself if the radius of curvature is the same as the separation distance. It should be for a lot of these questions, but doesn't have to be. The last thing, and this problem doesn't bring this up, but we're talking about orbits, is sometimes instead of asking about a specific speed of an orbit, they might want to know what the period of the orbit is. The period of the orbit goes back to talking about the radius of curvature because the period of the orbit is based on the circumference, the actual circle that the object is traveling through. Period is how long it takes to travel through that orbit. So these are the 3 things that get brought together in talking about orbit questions. Now this problem has a specific thing it wants. It's telling us that we're going to have a time of 3 orbits per day. So I guess we are going to have to use the period in this problem. And when we are dealing with a period problem, we have to combine all 3 of these things together before we can actually work on getting the answer. So let's start by combining these 2 things together. We've asked ourselves and answered the radius of curvature is the separation distance. So these are the same r. So I put m v squared over r equal to mc ms g over r squared. Now, subscript on this m. This represents the thing that's in orbit, and that will be the satellite. Next, and I don't make this clear, and I should. This is the inertial mass because it comes from Newton's second law. These are the gravitational masses. There is a definite point of our curriculum that wants to emphasize the difference between gravitational mass and inertial mass. Although they measure the same value, they do compare different things. Gravitational mass causes gravity. Inertial mass resists changes in motion. It's inertial mass in Newton's second law, and it determines the acceleration. So I want to be very clear that we need to recognize when we're dealing with inertial mass versus gravitational mass because AP wants us to recognize the difference. But they measure to be the same value, which means I can cancel it out. Which leaves me with v squared equals mcg over r, where mc stands for the mass at the center. Now that's my first set of substitutions. And yeah, I canceled one of the r's out too. The next substitution though is going to be to bring something in that has period. So that's another substitution. And that's, a lot of work. 2 pi r over t squared. Now, essentially we're done. We should clean this up though, make it look prettier. So I get 4 pi r squared over t squared equals mcg over r. Pledge of Allegiance. United States of America, to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. What? No lunch? Well, we don't know what we don't even know what bar it is. I don't know if we can go on today without knowing this. This bothers me. And we have to watch the morning show too. I'm not set up to watch the morning show, but I got an email that there's a morning show. So we'll make sure we watch the morning show tomorrow. Yeah. So because I haven't seen it yet. I mean, I got the email this morning when it came to work. Actually, I watched it. I'm on it. We want to definitely see it. It's really good. It's really good because it's got me in it. Anything with me in it's got to be at least mediocre. So let's just finish here because I want to get to this one part here because this is something that's not on the equation sheet, but it's something you might have to use. I just cross multiplied, but you might have to derive this on the exam. It has been on the exam like this before. And specifically, they want to have a comparison between the radius and the time. And it's here, this cube proportional to t squared. So you might have to get here on the exam. Now, once you get here, you have to know what to do with t. They say it makes 3 orbits in a day. At least mine does. Probably everybody's problem has a different one, right? So whatever yours is, you have to figure out what that means in time. There's 24 hours in a day. So if mine makes 3 orbits in a day, then that's 24 divided by 3 or 8 hours, which I'll have to convert to seconds before I can actually do the problem because everything in here has to be in seconds and meters. And that's because of this bad boy right here. He's in seconds and meters. So everything has to be in seconds and meters. So that's basically the question. Is there more you want me to talk about? All right. That's it then. So any further questions at home? I don't know when a bell rings, so. Well, I guess we have our answer. Well, guys, it's been real and it's been fun. If you have FSA tomorrow, have real fun. If you don't have FSA tomorrow, well, I'll be here for you. It'll be fun. So, bye guys at home. Have a good day.
Good day.